Welcome to Ready to Derive. In this video, we explore the ins and outs of the mean value theorem, an example of an existence theorem. An existence theorem basically guarantees that a function will achieve some attribute over an interval, but doesn't pinpoint where in the interval that might happen. Along the way, we'll briefly review the intermediate value theorem. That's the OG existence theorem that we met in the limits and continuity unit. Without divulging too much about the MVT right now because it will give away the punchline, I will say that the existence theorems are awesome because although the results seem self-evident, they are quite profound. So let's dive right in. So let's look at a scenario. So 1 p.m. you collect a ticket at a toll booth in order to get on the highway. This was before the time of electronic tolling. At 3 p.m. you exit the highway, a distance of 210 kilometers from where you entered. The toll booth operator collects the payment for the toll and then gives you a speeding ticket on top of it for going in excess of the speed limit of 100 kilometers an hour. So our job is to explain what is going on here. Well, we haven't got much to work with except the numbers in here. So what have we got? We have 1 p.m., 3 p.m., and we traveled a distance of 210 kilometers. So at least we could work out our average speed for the trip, which would be 210 kilometers. We traveled that in 2 hours, which means 105 kilometers per hour was our average speed, which technically is in excess of the speed limit, although barely. So let's have a look at this sort of visually. If we think about our trip, say, so this, the y-axis is distance and the x-axis is time. What we're actually doing when we work out the average speed of 105 kilometers per hour, we are actually working out the slope of a line connecting the points. What point? Well, this was at 1 p.m. and this was 3 p.m. And we know that 2 hours elapsed, and we're not sure what distance we were, say, from home at first and where we ended up, but we do know that this distance was 210 kilometers, and this is 2 hours. So what we're actually doing is working out just a rise of a run, a slope of this line, as if that yellow dotted line would be as if we just got on the highway, hit 105 kilometers an hour, and just continued on at that speed. But what was more likely to happen is that you would get on the highway and you'd kind of go at a slower speed to just, start speeding up. And then maybe you hit cruise control and you go at a constant speed for a while, and then you slow down to get off the highway. Now, what the mean value theorem says is that if your average speed is 105 kilometers an hour, there must be at least one time at which you were going at 105 kilometers per hour. So we were going at times slower, at times even faster, but there are a couple times, and if you stop for a moment to think about where this must happen, wherever the slope of the tangent line equals the slope of the secant line. So wherever these lines are parallel, so that looks like there and there, we were in fact speeding, going at 105 kilometers an hour. Now it could be that it only happens once if the curve was slightly different. So if our motion had looked like this, it might have happened only once, but the mean value theorem guarantees that it has to happen at least once over the interval. So let's look at a formal statement of the MVT using proper math speak and math notation. So there are a couple of conditions that have to be met for the theorem to apply, and they are that f is continuous on the closed interval AB and differentiable on the open interval AB. Now we'll explain kind of the closed interval, open interval a little later in the video, but let's just have a look at a function that is definitely continuous over, let's call that A and that B. And it's differentiable in that there's no discontinuities or corners or cusps of any sort. So if this is true, then the mean value theorem guarantees that there's at least one number C in the open interval AB for which the following is true. Now, what is the following? Let's look at the right-hand side first. The right-hand side, f of B minus f of A. So if this is A, then this must be f of A, and B must correspond on the y-axis to f of B. And then fb minus f of A is just the rise, B minus A is the run. We are just working out the slope over the line connecting the endpoints of that interval, which is the slope of the secant line. Now, what about here on the left-hand side? F prime represents the derivative, which is the slope of the graph at any point. So what it's saying is that the slope at some point, at least one point on the graph, the slope has to equal the slope of the graph has to equal the slope of the secant line. So it looks like there's one point there where this tangent line is parallel. And in this case, there seems to be another point, another value of c, let's call that c2, at which the slope of the tangent line is parallel, or sorry, is equal to the slope of the secant line. And the lines therefore are parallel. Now, the mean value theorem is very mathematical in its description, and it's sometimes easy to forget what the quantities that we're interested in represent. So let's just kind of review again the mean value theorem, but really sort of bring in more kind of contextual language. So here's our function, and we are told that this quantity, f of b minus f of a over b minus a, what is this quantity again? Let's make sure we understand that we can refer to this as the slope of the secant line over the interval ab. So that would be this line here. And remember, now in this case, this is a, this is b. We usually think as a being the smaller number, b being the larger, because we write it in that alphabetical order, ab. The slope of the secant line, but let's tie this back to the original scenario we introduced. It's also the average rate of change of the function over that interval ab. And we are told that that is equal to f prime c at least once. At least once that will be true. And what is f prime c? That is the slope of the tangent line at some value c in the interval. So remember, this is all, the mean value theorem, all it just says is that it guarantees that that value c will be in the interval ab. And the slope of the tangent line at x equals c, again referring back to our original example, is really the instantaneous rate of change of f at x equals c. So that was our instantaneous velocity, whereas the secant line represented our average velocity. And moving forward, just so we don't have to kind of say all these words, we're going to refer to average rate of change as AROC and instantaneous rate of change as IROC, just so we don't have to keep writing all that out. So let's look a little more closely at why the conditions must be met for the mean value theorem to apply. So why continuous? Why must the function be continuous? Well, let's look at a situation where the function has a discontinuity at some point. Would the mean value theorem apply? So take this example here. All right, so the yellow dotted line is the secant line, and we can see we do feel that there is a point. It seems like if we could draw a line here, a tangent line, that there would be that would be parallel to the secant line, but because there's a discontinuity, no tangent line exists, and the mean value theorem does not apply. All right, so what about differentiable? Why not just continuous? Well, let's look at this situation. Here is a function that's continuous but not differentiable. And if we look at the slope of that secant line, if we gave that secant line kind of a value, let's say looks like a slope of 1 here. Well, this portion of the graph looks like, of the function f, looks like it has a slope of 2, and this is negative something, maybe negative a fifth. So there is no point at which the slope of the function is equal to 1. You might be tempted to think, well, maybe here I could just draw a tangent line there that looks like it's parallel. But in fact, right there, where would the tangent line go? This is a corner, and as we know, a function is not differentiable at the corner because there's no clearly defined tangent line. So therefore, the mean value theorem cannot apply. So your next question might be, well, why both continuous and differentiable? Isn't it enough just to have f be differentiable on AB? I mean, we know the theorem from early in the course that says differentiability implies continuity. So isn't that sufficient? Well, let's have a look at this situation. Let's see if we can find a counterexample that will make the mean value theorem not apply. So here's a function that's differentiable on the open interval AB. It's not continuous along there, but it is differentiable on that open interval. So we could consider this scenario, and then if we, let's see, we need to have the function defined at b. So we have here, this would be b comma f of b, and this here would be a comma f of a right here. So if we work out f of b minus f of a over b minus a, we would actually be working out the slope of that line there, connecting the endpoints, the secant line. And as you can see, that slope is negative, but meanwhile, the function itself is increasing and is positive. The slope is positive. So there's not one point on that function where the slope of the tangent line equals the slope of that secant line. So therefore, that is why we need this extra condition that f has to be continuous on the closed interval ab. Now, just as an aside, it is possible that the function could have done this. So it could have done the same thing, but looked something like that. So, and then you could argue, well, look, there is a point where the slope of the tangent line equals the slope of the secant line. But the problem is that it can't be guaranteed by the mean value theorem because of the counterexample we just looked at. Now you could change your interval over which and look over a smaller interval and then use the mean value theorem to find that or guarantee that. But you need both conditions in order to be able to apply the mean value theorem. So let's do our first example. The Bay of Fundy in Canada is renowned for having the world's largest tidal variations, and the following table shows the height of the tide every 4 hours over a 24-hour period. This is actual real-world data. This is not made up. So I got this from the internet. So anyway, here's a nice practical application of the MVT. So assuming tidal height is both continuous and differentiable, which seems fair to assume, what is a conclusion you could derive using the MVT? Well, this is very open-ended. We get to kind of pick our interval. So let's pick this interval. Let's make A 8 and B 16 and sort of see what happens over this interval. So using common sense or the formula, we could find the average rate of change of the height over that interval. So using the proper notation, we're going to work out this. H of 16 is 6.2. H of 8, the height at 8 hours, is 1.4 over a difference of 8 hours. So that means that we have the height of the tide changed 4.8 meters, which is quite a lot over an 8-hour period, which means that the average rate of change of the height was 0.6 meters per hour. And what the mean value theorem guarantees is that at some point, C, in that interval 8 to 12, the instantaneous rate of change of the height of the tide would have to be 0.6 meters per hour. And we know that C has to be in the interval 8 to 16. So C is in that interval, open interval, 8 to 16. So in words, in the context of the problem, the MVT guarantees that there exists at least one time between 8 a.m. and 4 p.m. at which the instantaneous rate of change of tidal height was equal to 0.6 meters per hour. So example 2. Now let's determine if the mean value theorem can be applied to this function over the interval, closed interval 0, 4, and if so, find all possible values of C. So we need to train ourselves to make sure the conditions are met at first, because sometimes they're not, and the mean value theorem can't be applied, as we saw. So the conditions, well, if we look at the function 3 plus rad x, that's made up of two functions, y equals 3 and y equals square root of x, and we know that they are both continuous functions over the interval, closed interval 0, 4. And if they are, because all rational functions are continuous, this is from earlier in the course, and y equals 3 is a constant, so therefore the sum of the functions f of x will be continuous also. So continuity, check. Now, what about differentiability? Now, if this is the derivative of the function, it's 1 over 2 rad x, and we can see that, that actually, it is not differentiable at x equals 0. I mean, x can't be negative, but that's okay. That's not the interval we're interested in. We're interested in from 0 to 4. So we have a little problem because it seems it's not differentiable now at x equals 0, but that's okay because it is differentiable over the open interval 0 to 4. That's all we need to apply the mean value theorem. So the next step would be to find the AROC, the average rate of change over the interval. So that would be f of 4 minus f of 0 over 4 minus 0. And f of 4 works out to be 5. F of 0 is just 3. And that works out to be 1/2. So the average rate of change over that interval is 1/2. And then the last step is to find c. Well, we know that that average rate of change of 1/2 has to be equal to f prime c at least 1 point in the interval. So we can just replace f prime with 1 over 2. Now you could leave x in there. You don't have to write c, but if it helps to think that you're really solving for a particular value or 2, it might be good to do this. And if you cross multiply, you get this. And we find out that the answer is c is 1. So, and 1 does fall in the interval 0 to 4, as was guaranteed. And we therefore know that f prime of 1 will equal 1/2. So let's look at another example. Let's look at this function, cube root of x over the interval -1, 1. See if the mean value theorem can apply. So the conditions. So rational functions are continuous over their domain, and the domain of a cube root function is all real numbers, so we definitely know it's continuous over -1, 1. So let's look at differentiability. And we would rewrite this as x to the 1/3 and take the derivative using the power rule, and we would get this. So that would be 1 over 3 times the cube root of x squared. Now, so what about differentiability? Well, we notice that x equals 0 is a problem because x is now in the denominator of the derivative function. So it means f prime of 0 does not exist, which means f is not differentiable over that interval, and therefore we cannot proceed with the mean value theorem. Now let's look at a picture of this to sort of make it more real. So the MVT cannot be applied, but if we look at this, at the function, the cube root function, we see that at x equals 0, and this is the problem, we have a vertical tangent line at x equals 0. So that means it's not differentiable there. But we could say, well, look, it doesn't mean that the result isn't, that it cannot be derived at some point. So let's look at this value here. It looks like the slope of the tangent line equals the slope of the secant line there, and here as well. But we just can't establish that using the tool of the mean value theorem. Once again, we could change the interval over which we are interested, at changing the interval to make sure that the conditions are met, then guarantees the mean value theorem can be applied without having to even look at a sketch of the situation. So, so always, the moral of the story is always check the conditions first. So sometimes students get a little confused between the mean value theorem, the intermediate value theorem. They're both existence theorems, but they have kind of different conclusions, and they're both very important. So let's look at the Bay of Fundy problem again, just to kind of say, what would the intermediate value theorem tell us about how this function is behaving? And let's just pick the same time interval again. Let's look from 8 to 16. So let's see, at 8 hours, or at 8 a.m., the height of the tide was 1.4. So this would be height, and this would be time. And at 16, the height was up here at 6.2. And we know, and the only condition for the intermediate value theorem is it's just that the function be continuous. So that's one sort of main difference. But what the intermediate value theorem says is that once you've established your range of y values, so we know that the height of the tide goes from 1.4 meters up to 6.2. And then what this guarantees is that it says, well, for any, pick a y value, any y value between the two y values at the endpoints. So we could say 5.8, just make up any y value that falls in the range 1.4 to 6.2. What the intermediate value theorem, notice there's no averages in here, there's no means. All it says is that, look, it must have become 5.8 at some point in the interval 8 to 16 if the function is continuous. So what it guarantees is that h of c is equal to whatever value, in this case 5.8. Notice that's very different from the mean value theorem, which talks about what does h prime of c, what value would h prime of c assume over that interval. So that's the main distinction between the two. We showed before, let's just recall, we showed that there was a c. It's not the same c, by the way, but we showed from the mean value theorem, basically says that h prime c would have to equal 0.6 meters per hour at some point, and the IVT says that there is some value at which the height was equal to 5.8 meters. So there's a lot of things you could also have established that there's some other time at which the height was 2 meters. What the IVT says you can't do, though, is you can't pick a value outside. So pick a value outside the interval. So I can't say that at 1 meter, there's no guarantee that the height of the tide was 1 meter in that interval 8 to 16. So let's end with one example that kind of mixes and matches the IVT and MVT so we can learn to distinguish when we use which. So when your G satisfies the conditions for both theorems, and we only have information about the endpoints right now. We don't even know what the function is. But with these type of problems, it's always good to start by graphing the endpoints. So we know that at -1, G is 7, and at x equals 4, G is 2, so we have 2 points that we can graph, the endpoints of the interval. So -1, 7 goes from a high of 7 down to a low of 2. And the function is continuous and differentiable in there. And so we have to determine if each statement can be established using either the IVT or MVT. And the statements, each one begins with, there is at least one c in the interval, -1 to 4, for which. So let's look at the first one. G of c equals 7. Well, 7 is up here. And right now, the way I drew the function, it doesn't look like it ever gets back up to 7. There's no guarantee just because at the end, it's the endpoints are at -1, it's 7. But who knows? It could have looked like this. But the IVT is very specific that the value you choose, the y value you choose, has to be strictly between the endpoint y values. So unfortunately, 7 is right there on the cusp, so there's no guarantee. We cannot establish that G of c ever equals 7 again in that interval. On the other hand, G of c equals 5. So 5 looks like it's around here maybe, and we can see that, wow, because 5 is between 2 and 7, look, there is definitely a value of c for which that is true. So this would be true by the IVT, the Intermediate Value Theorem. Now, for C and D, we're dealing with primes. The minute you see primes, derivatives, you know you're dealing with the Mean Value Theorem. And before you go even any further, you should work out the AROC. And the AROC is the change in y over the change in x. That comes out to be -1. And now that's fixed. That's the average rate of change over the interval. Remember, that's the slope of the secant line. So therefore, we know that the instantaneous rate of change will equal the average rate of change at some point in that interval. And this is true by the mean value theorem. Now, G prime of C equals 0. Well, the mean value theorem is very specific. We can only establish that equals -1. It may equal 0. So look, and if the function was the green function, there was a point where the derivative was equal to 0, but not for the blue function. There's no guarantee, so we cannot establish this statement. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.